My name is Andrew Bogart, and me and Jennifer Mulligan are going to do a presentation over grading monochrometers.
Just as sort of an overview, a grading monochrometer is the part of a spectrophotometer that separates different wavelengths from one another and selects a narrow band of wavelengths to pass through the sample. Here are some examples of gratings. They're used to diffract the light in a monochrometer, and we'll talk more about how they work in a little bit.
I'm going to talk to you about how this grading monochrometer works. We have a focus light source coming in, which is white light coming into this entrance slit, and this light is going to be collimated when it hits this mirror and become parallel. And once it hits that mirror, it's going to be reflected off the mirror onto the grating, and then the grating, it works a little different. I'll talk to you more about that in a minute. And then after it hits this grating, it's going to be sent to another concave mirror, and after that concave mirror, it's going to come out the exit slit, which, as you can see, when it comes in, it's white light, so we have many different wavelengths and colors of light. And when it comes out of this exit slit, there's just one color. And here's a little more about the grating. The grating has many sawtooth edges, as you can see here. And when the light comes in, it's going to be reflected off of these at different angles. So it's not going to be all parallel, and that's how we separate it. And then this grating is going to have 600 to 2400 grooves per millimeter. And that's a whole lot of grooves if you think about it for that short amount of distance. And these grooves here are equally spaced and parallel. Now Jennifer's going to talk to you about diffraction.
Alright, when light is reflected, each groove behaves as a source of radiation, diffracting in all directions, which creates constructive and destructive waves. Each color has different wavelengths, so the rays don't all have constructive waves, and therefore the waves separate in space. In order to get a different wavelength to pass through the exit slit, the grating is merely rotated. For interference, if the adjacent light rays are in phase, they're reinforced in each other, which leads to constructive interference, as shown here. And if they're out of phase, they cancel each other out, creating destructive interference. The grating is like a series of tiny mirrors. Light emanates from each spot, and the waves can interfere at different distances from the grating. The constructive interference of different wavelengths occurs at different spots at the focal plane of the exit slit, which is why the color separation occurs.
I'm going to talk to you about the grating equation. And for each incident angle theta, there are diffraction angles phi at which a given wavelength will produce maximum constructive interference. Therefore, filters that reject many wavelengths are used to select a desired wavelength and reject other wavelengths. Some types are absorptive and interference filters. And this right here is an example of the white light spectrum that would enter through the entrance slit and what it would look like through the exit slit as monochromic light.
Some applications of monochrometers are automatic scanning spectrophotometer, which includes a mechanism to change the wavelength selected by the monochrometer and to record the resulting changes in the measured quantity as a function of the wavelength. Absorption spectrophotometers measure the absorption of light by a sample as a function of wavelength. Monochrometers are also used in optical instruments that measure other phenomena besides simple absorption or reflection, wherever the color of the light is significant variable. For example, circular dichroism. Lasers are also used for this, and monochromatic light allows for the measurement of the quantum efficiency of an imaging device. And here is an example of a spectrophotometer.
Thank you.